Imagine turning iron into gold. Sounds like fantasy, right? But that obsession, that crazy dream, is exactly what gave birth to the science we now call chemistry. Hi everyone, welcome to the Chemstore. I'm your teacher Judy, and today we start +1 chemistry, chapter 1, some basic concepts of chemistry. Every single day, chemistry is happening around you. Milk turning into curd, iron slowly rusting, sugarcane juice becoming vinegar over time. These are all chemical changes. So what exactly is chemistry? Chemistry is the branch of science that studies the preparation, properties, structure, and reactions of material substances. In simpler words, it is the science of atoms and molecules. Now here is something most students don't know. Chemistry as we know it today didn't start in Europe. India was already way ahead. In ancient India, chemistry was called Rasayan Shastra. Excavations at Mohenjo-daro and Harappa show remarkable achievements. People were making baked bricks, producing glazed pottery, and extracting metals like copper, gold, and silver. Nagarjun, a brilliant Indian scientist, wrote Rasratnaka. Chakrapani discovered mercury sulfide and is even credited with inventing soap. And Acharya Kanda, born around 600 BCE, proposed the idea of tiny indivisible particles he called Parmanu, what we now call atoms, almost 2500 years before John Dalton. Chemistry also developed through alchemy, that early tradition of trying to convert metals into gold, and iatrochemistry, which was chemistry applied to medicine between 1300 and 1600 CE. Modern chemistry as a formal science took shape in 18th century Europe after Arab scholars brought alchemical traditions to the West. By the mid-1800s, European scientists began arriving in India too, and modern chemistry started growing here as well. This global exchange of knowledge laid the foundation for the chemistry we study today. Now you might be wondering, why should I care about chemistry? Here's why. Chemistry produces life-saving drugs like cisplatin and Taxol, used in cancer treatment. It gives us fertilizers that feed billions of people. It helped create superconducting ceramics and optical fibers that power the internet. And chemists even developed safer alternatives to CFCs, the chemicals that were destroying our ozone layer. So chemistry is not just a subject. It is everywhere around you, every single day. That's it for the introduction. Now you know what chemistry is, how ancient India contributed to it, and why it matters in real life. In the next section, we go deeper, the 3 states of matter and how substances are classified. Let's start. Look around you. The phone or laptop you are watching this on, the water you drink, the air you breathe, what do they all have in common? They are all made of matter. So, let's start with the basics. Anything which has mass and occupies space is called matter. Everything around us is composed of matter. Matter can exist in 3 physical states: solid, liquid, and gas. In solids, particles are held very close to each other in an orderly fashion, meaning they have a definite volume and a definite shape. In liquids, particles are close but can move around. They have a definite volume but do not have a definite shape. They simply take the shape of whatever container you pour them in. In gases, particles are far apart and move fast. They have neither definite volume nor definite shape, completely occupying their container. And the best part? These states are interconvertible. By simply changing the temperature and pressure. Heating a solid melts it into a liquid, and heating it further boils it into a gas. So far, we've looked at matter from a microscopic, molecular perspective, how individual particles move and interact. Now, let's zoom out to a macroscopic or bulk level. How do we classify the matter we see and interact with every day? At this macroscopic level, We classify all matter into two main categories: mixtures and pure substances. Let's focus on mixtures first. A mixture contains particles of two or more pure substances in any ratio, meaning their composition is variable. Mixtures can be homogeneous or heterogeneous. In a homogeneous mixture, like sugar solution or air, the components completely mix. The particles are uniformly distributed, and it looks the same throughout. But in a heterogeneous mixture, the composition is not uniform. Think of a mixture of salt and sugar, or grains mixed with dirt. You can visibly see the different components. And remember, you can separate mixtures using simple physical methods like handpicking, filtration, or distillation. On the other side of our chart, we have pure substances. Unlike mixtures, pure substances have a fixed composition. These are further divided into two main categories: elements and compounds. Particles of an element consist of only one type of atom, like solid sodium, copper, or oxygen gas. But when two or more atoms of different elements combine in a definite ratio, they form a compound, like water or carbon dioxide. Here is a fascinating fact for your exams. The properties of a compound are totally different from its constituent elements. For example, hydrogen burns with a pop sound, and oxygen supports combustion. But when they combine to form the compound water, we use water as a fire extinguisher. That wraps up our look at the states of matter and classification. Now that we know what matter is, how do we actually measure it? So, we know what matter is. But chemistry isn't just about looking at matter. It is about measuring it. To do any real science, we need to quantify physical properties like length, area, or volume. And to make sure a chemist in India understands a chemist in France, we use a universal standard. We call this the International System of Units, or SI units. The SI system is built on 7 base units. For length, we use the meter, m. For mass, the kilogram, kg. For time, the second, pes. For electric current, the ampere, A. For thermodynamic temperature, the Kelvin, K. For the amount of a substance, the mole, mol. And for luminous intensity, the candela, CD. But atoms are incredibly small, and the number of atoms in a single drop of water is massive. To handle this, the SI system allows us to use prefixes to indicate multiples or submultiples of a unit. For example, a kilogram means 10 raised to 3 grams, while a milligram means 10 raised to minus 3 grams. And when we measure things at the atomic level, we often use nano, which is 10 raised to minus 9. Now, let's clear up a massive misconception. Mass and weight are not the same thing. Mass is the amount of matter present in a substance, and it is totally constant. Weight, however, is the force exerted by gravity on an object. For example, if an astronaut stands on Earth and then floats on the moon, your mass is the exact same in both places, but your weight changes because the gravity changes. In the lab, we determine mass accurately using an analytical balance. We also frequently measure volume, which is the amount of space a substance occupies. While the strict SI unit for volume is the cubic meter, chemists usually work with smaller amounts. We commonly use the liter, L, or milliliter, ml, for liquids. And when you divide a substance's mass by its volume, you get its density, which tells us exactly how tightly packed its particles are. Finally, let's talk about temperature. In chemistry, we commonly use 3 different scales to measure it. These are degrees Celsius, degrees Fahrenheit, and Kelvin. Among them, Kelvin is the official C base unit. Interestingly, while you can easily have negative temperatures on the Celsius and Fahrenheit scales, On the Kelvin scale, negative temperatures are completely impossible, starting at absolute zero. If you need to convert between these scales, keep these formulas handy. To get Fahrenheit from Celsius, use the formula Fahrenheit equals 9/5 of Celsius plus 32. And to get Kelvin from Celsius, it's even simpler. Just add 273.15. So, now we have the right units and formulas to measure our chemicals. But what happens when our measurements aren't perfectly exact? Or when we need to write out a number with 20 zeros? In our next segment, we are going to tackle how to handle messy, real-world data using scientific notation and significant figures. Let's get into it. If you look at past year papers, this next section is a high-weightage practical topic. In chemistry, we deal with things that are incredibly tiny, like the mass of a hydrogen atom, and numbers that are massively huge, like the amount of molecules in a glass of water. Writing all those zeros out is a nightmare, and calculating with them is even worse. So, how do chemists handle messy, massive numbers? We use scientific notation and significant figures. Instead of writing endless zeros, we use exponential notation to simplify massive numbers. Any number can be represented in the general mathematical form n times 10 to the power of n. Here, n is the coefficient. It must be a number between 1.000 and 9.999. And n is the exponent, an integer which tells us exactly how many places the decimal has moved. For example, if we have a large number like 232.508, we move the decimal 2 places to the left, so it becomes 2.32508 times 10 to the power of 2. Now, if we have a tiny number like 0.00016, we move the decimal 4 places to the right, giving us a negative exponent, 1.6 times 10 to the negative 4. This transformation makes complex calculations like multiplication and division so much easier. But what about accuracy? Every single measurement we make in the lab has some degree of uncertainty. To show exactly how precise a measurement is, chemists use significant figures. These are all the meaningful digits which are known with certainty, plus exactly one final digit that is estimated. Mastering them is crucial. There are 5 golden rules you need to memorize. Rule 1. All non-zero digits are significant. For example, in 285 centimeters, all 3 digits are non-zero, giving us 3 significant figures. Rule 2. Zeros preceding the first non-zero digit are not significant. They merely locate the decimal point. So in 0.03, there is only one significant figure. Rule 3. Zeros between 2 non-zero digits are significant because they are trapped between non-zeros. Therefore, 2.005 has exactly 4 significant figures. Rule 4. Zeros at the end of a number are significant only if there is a decimal point. For example, 0.200 grams has 3 significant figures because the decimal point activates those trailing zeros. But the number 100, without a decimal point, it only has one significant figure. Rule 5. Counting objects, like 2 balls or 20 eggs, are exact numbers. Because there is no uncertainty in counting, these exact numbers have infinite significant figures. Finally, when calculating, we often need to round off our answers. Most of you know that if the last digit is more than 5, you round up. And if it's less than 5, you keep it the same. But what if the digit to be removed is exactly 5? This is where we apply the chemist's rule of 5. Look at the preceding number before the 5. If it is even, leave it alone. If it is odd, increase it by 1. For example, let's round 6.35. The preceding digit is 3, which is odd. Therefore, we round it up, and 6.35 becomes 6.4. Now look at 6.25. The preceding digit is 2, which is already even. So we leave it alone, and 6.25 rounds off to 6.2. That's it for part 1. We've covered everything from the ancient roots of chemistry to mastering significant figures. If you found this helpful, hit subscribe and join the TheChemstore. Drop a comment below if you have any questions, and be sure to check out our website in the description for more resources. See you in the next video.